So now we'll look at Laplacian, the Laplace operator in other coordinate systems. So if we apply the chain rule to polar coordinates, whoops. So r is the square root of x squared plus y squared, and theta, the argument, is arctangent of y over x for the appropriately chosen branch of the arctangent function. Then this will result in uxx plus uyy becoming second partial with respect to r plus 1 over r first partial with respect to r plus 1 over r squared second partial with respect to theta. And then for cylindrical coordinates, the third coordinate z is just parameterized by itself. So what happens is we get the same formula from the previous line, but then we just tack on a second partial with respect to z on either side. Okay, and then there's also spherical coordinates. And so the calculations with the chain rule, that's just straightforward differentiation. It's written up in detail in the text. I will spare you the gory algebra for now. For spherical coordinates, so we've got x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. Okay, so again, using chain rule with these hairy coordinates, we end up with the Laplacian of u is the second partial of u with respect to rho plus 2 over rho first partial with respect to rho plus, and then we've got 1 over rho squared sine phi times u sub phi sine of phi differentiated with respect to phi plus rho squared sine squared phi in the denominator times the second partial of u with respect to theta. And so I'm also going to spare you the derivation of that one. It's long and tedious and not especially insightful. But let's see how to use something like this. So suppose we've got a problem where we're looking at the steady state temperature between two spheres. Okay, so we'll say that the sphere at rho equals 1 is kept at 0 degrees, and the sphere at rho equals 2 is kept at 10 degrees. Okay, so this problem is going to be is clearly independent of phi and theta, because the boundary conditions are constant all the way around these boundary spheres here. So so Laplace u equals 0 takes the form second derivative of u. Well, u is just going to be a function of rho alone, so let's write it with primes as an ODE. And so we have u double prime plus 2 over rho u is equal to 0. Since everything in there has been differentiated at least once, we can reduce the order really easily by putting v equal to u prime. And then it becomes v prime plus 2 over rho v equals 0. This is a first order linear ODE. It's also a separable ODE, so you can solve it using either method just for fun. I'm going to do it with the integrating factor. So my integrating factor mu is going to be e to the integral of the coefficient of v, so that's 2 over rho. And so that's going to be e to the 2 log rho, which is rho squared when you simplify. So multiplying this equation across by rho squared, I end up with rho squared v on the one hand side, and on the other side 0. So that's just using product rule. And so then rho squared v is going to be some constant, let's say a. And so v is a over rho squared, but v was u prime, so I have to integrate again. So u is going to be some constant a over rho plus some other constant b. And so I'm aware that those two a's are different, but that's perfectly fine. It's just some arbitrary constant. Now I can find a and b using the boundary conditions. So if we evaluate at on the sphere of radius 1, then it's equal to 0 there, and our formula for u gives us a plus b. So that tells us that b is equal to negative a. And if we look on the other sphere where it's kept equal to 10, so that's at radius 2, then this is a over 2 plus b, which we just saw is a over 2 minus a, which, and that, so that's coming from this guy here. And so this is minus a over 2. And so cross multiplying, we get a is equal to negative 20. So u of rho is going to be 20 minus 20 over rho, which you can check satisfies the problem just by inspection. Definitely when you take its second derivative with respect to rho, it's going to vanish. And the boundary condition. Yeah. So when you evaluate that on the boundary, you can see that that definitely gives you 0 when u is equal to, when rho is equal to 1, and it gives you 10 when rho is equal to 2.